we're looking at a two-sample independent problem where we're going to do a hypothesis test. Now remember, two-sample independent problems means that the first sample doesn't at all affect who's in the second sample. So you won't see words like matched pairs or before and after, things like that. And a lot of times a nice quick way to tell that you're in a two-sample independent is like in our case right here, that the sample size are different. So as you can see, this sample right here, size is 7. This sample right here is size 8. So there's a difference in their sample size. So that's one clear indication that we're in a two-sample independent problem. So we're asked at a 0.05 significance level, is there sufficient evidence to support that there's a difference in blood pressure for patients that use Med A and blood pressure for patients that use Med B? So we're just looking at a difference in their blood pressures after taking this blood pressure medicine. So when we're in a two-sample problem, we have to make sure all our conditions are met before we can use the technique that we have learned. The first thing we have to look for are the samples randomly selected. And like I said, in our class, we're going to assume that they're randomly selected, that we have a simple random sample or randomized experiment. In this case, this is a randomized experiment. We took patients, you're not seeing that in how it's written, but patients that had high blood pressure were randomly assigned to medicine A and medicine B. So the first condition is met, as it always is in our class. So like I said, our first assumption met. Samples are obtained either by a simple random sample, that's SRS, or randomized experiment. The second is that my sample size is small compared to the population. And we said we always assume this to be true in our class. Now the third assumption that has to be met is normality of the sampling distributions for both the first sample and the second sample. This is the one you have to check. So you check if the sampling distribution for the first sample is normal or approximately normal, just like you would for one sample. So you either have a sample of 30 or more, where you can evoke the central limit theorem, because we said 30 is our magic number in our class. And then if we're told that the population it comes from is normal, then any sampling distribution of any size would be normally distributed. But if our sample is less than 30, which is in our case, we would have to do a data analysis to make sure it was normally distributed. And then we'd also have to do that extra check, since our sample size is so small, to make sure there are no outliers. We do that for the first sample. Then we have to make sure the sampling distribution for the second sample is normal or approximately normal. So we do the same thing for the second sample. We either look for the sample size to be 30 or more. If we're told that the population that sample 2 came from was normal, then any sample size would make the sampling distribution normal. Or if our sample size is less than 30, we have to do a data analysis, which is what we had to do in this case. So our first sample was a sample of size 7, definitely small. But we do the probability plot, and there's no major deviations from a linear. Remember, our probability plots, our data should run along a line, and ours looks like it is. Nothing looking too egregious from that, so not bad at all. And we also see that there are no outliers, because our sample size is so small, any outlier would greatly affect the mean and would affect our technique. So sample 1 looks good, but we're not done yet. We also have to make sure that sample 2 is normally distributed with no outliers, and we look at its probability plot, and again, doesn't look bad at all, and no asterisks here, so that indicates that there are no outliers for sample 2. So all our conditions are met. Now, so now we're ready to start our technique for our hypothesis test. So the first thing is we have to write the null and alternative hypothesis. Well, we're going to assume that the mean of sample A, people that took Med A, minus the mean of sample of people who took medicine B, they're equal. So if I subtracted the two, it would be 0. The alternative is we're just seeing if there's a difference. So mu A minus mu B just doesn't equal 0. There's a difference between the two, and we want to look for that. So that's the first step, is writing the null and alternative. And I said another way you could have written it was mu sub A equal mu sub B. That's perfectly fine. Or mu sub A just doesn't equal mu sub B. That's an alternative way to write the null and alternative hypotheses. My alpha, my significance level is 0.05. Step 3. Now, this is where we get our test statistic. Since we don't have a population standard deviation for either of our samples, and even if we didn't have it for one, we have to go and use the student t-distributions after we standardize. So we get a test statistic, or a t-naught. I call it t-naught because it's the test statistic that we're getting. We're standardizing in the using the null hypothesis mean, which in our class, the value in the null will always be 0. In my introductory stat class, we always use 0 in the null as we teach this. So the test statistic will be the difference of your first sample from the second sample. Now you could do the second sample, x sub b minus x sub a. That's perfectly fine. You'll just get, a test statistic with the opposite sign. But so it doesn't matter which one you do. I'll generally guide you to that so that we all have the same test statistic and all that good stuff. So minus mu A minus mu B. But we know in our class this is always 0. And then the standard error, and this was the new thing we talked about, the standard error for the difference of two means looks like this. The standard deviation from our sample, I square that, or the variance, and I divide that by the sample size for my first sample that took med A. The standard deviation of those who took medicine B, their blood pressure, divided by its sample size. So that's the standard error when we have a sampling distribution of the difference of means and all our conditions are met. We can say it's normally distributed, and we'd say mu1 minus mu2 is the mean, because the mean of that sampling distribution of the difference of the means for the independent case. And the standard error is sigma squared, not sigma 1 squared over the sample size of our first sample, plus the variance of our sample 2, or the standard deviation squared of our sample 2 divided by its sample size. But when we don't know what sigma is, and we have to estimate it with sample standard deviation, that brings us into the student t distribution, and that's why our standard error has sample standard deviation instead of sigma. Now step 4 is to find the critical value, because remember, when we are in the student t table, when we first learn it, we use the classical method. So we need to find the critical value. And to find the critical value, you have to look at your alpha and your degree of freedom. And remember how we found degree of freedom? It was always n minus 1. But look, I've got 2 n's now, and they can be different. So how do I determine the degree of freedom? And I said, well, there is a equation, a Satterwhite's equation, and it's a little involved. So we're going to use the conservative method to find the degree of freedom for a 2-sample problem. So for a 2-sample problem, we'll use the conservative method. Take the smaller sample size and subtract 1. And that would give you the degree of freedom. And the shorthand way to write that is the degree of freedom equals the minimum of n1 minus 1, n2 minus 1. So in other words, you find the smallest sample size, subtract it from 1, and that would be your degree of freedom. So in our sample, the smallest sample size is 7. So my degree of freedom is 6. My alpha in this problem is 0.05. Now to find the critical value, I have to pull up the student t distribution. So the student's t table looks like this. And the way that we use it to find here's our student's t-table. And this is how we find the critical value for confidence intervals. So if I wanted a 90% confidence interval, degree of freedom of 6, I would just go along here and find my critical value. But for hypothesis testing, this is what we do. We look for our alpha. These are alphas here. This right here is alpha. So these are alphas. So you say, well, why 2 lines? This one is for a two-tailed test. We look in this row. We look at that last row. For our one-tailed test, our right-tailed and left-tailed, we look for the alpha on this row right here. But in our problem, we are looking at this row because we're in a two-tailed test, remember? We're looking to see if there's a difference in the mean. So that's where we're looking. So degree of freedom of 6, alpha of 0.05. So when I go to my chart, alpha of 0.05, my degree of freedom is 6. So I look where these two collide, and that would be my critical value that I would use. And since it's a two-tailed test, I would say critical values. So plus or minus 2.447. So again, I have 2 critical values, 2.447 and negative 2.447. So the first thing I need to do, now that I've got that, and then I can determine whether to reject or not reject. So let's take a look at this specific problem. To get this test statistic now, I can start to put in my numbers, and then I can look at my critical values in order to reject or not reject. So in this test statistic, the mean of my first sample, the people that took medicine A, is 133.1429. I subtract that from the mean for people that took medicine B, 124.875. Then I divide it by, and in the square root, I put the standard deviation for people that took medicine A, 12.3211. I square that value and divide by the sample size, which is 7. But I have to add that to the variance or the standard deviation squared of those that took medicine B, divided by 8. So I have to do all that underneath the radical. When I do that, I get the test statistic of 1.614. So when I put all that in my calculator, I get 1.614. Now, how do I use that to determine whether I reject or not reject? Well, this is just like all the other hypothesis tests that we've done. So to determine whether to reject for a two-tailed test, remember, if my test statistic is positive, then the criteria for rejection is that my test statistic should be greater than the positive critical value. Now, if my test statistic is less than 0, in other words, if my test statistic were negative, then the criteria for rejection would be my test statistic should be less than the negative critical value. Well, my test statistic is positive, so I'm in this case right here. So is my test statistic 1.614, is it greater than the positive critical value, 2.447? And the answer to that is no. It isn't greater. If it's not greater, I cannot reject. So based on this, I do not reject the null hypothesis. I don't have enough evidence to reject the null hypothesis. Therefore, I would write as my conclusion, in the context of my problem, at a 0.05 significance level, there is insufficient evidence to support the claim that drug A blood pressure is any different than the blood pressure of people that took drug B. So That's how you would do a two-sample, independent problem. At least one example. And this was for a two-tailed test. Thanks for watching.